Hello again, good morning, good afternoon or good evening whenever you may be watching this. This is going to be the last lesson on the differentiation topic for year 12. I've called it Pure Chapter 12.7. So we're going to be talking through what we mentioned in 12.6, which is quite a long video, and as well some of the concepts there I did get on to talking about for quite some time. So if the last video confused you, I've put a bit more effort into this one in terms of clarifying the main points from that one in preparation for these exercises. So if you're slightly confused or unsure about the last video, hopefully this one will make the previous one make more sense to you. So anyway, we're going to start off, as you could probably guess, with the 4 warm-up questions. Here they are. If you've got this printed out, great stuff. Attempt these now and then play the video afterwards. If you've not got a printout, copy these down, have a go, and then play the video when you're ready. Okay, so let's have a look at some of these solutions. So the first one, we have a rectangle, and we want to prove that y equals 10 minus x, given that the perimeter is 20. So just going back to the basics from GCSE, we know what the perimeter of a rectangle is. The perimeter, let's call it P, like we have done here, is going to be 2 lots of the length, which is 2x, plus 2 lots of the width, which we've called here y. So substitute in what we know. We're told that the perimeter is 20. So in our case, P, we can substitute in 20 for the value of P. So 20 equals 2x plus 2y. We can then divide through by 2, which gives us 10 equals x plus y. Therefore, if we just subtract x from both sides, we'll get what we want to get. So y equals 10 minus x, which is what we wanted to prove all along. And so that's question 1, done and dusted. Question 2, we're going to use the answer from question 1 to show that the area of the rectangle is 10x minus x squared. Well, as we know, again from GCSE or even earlier, the area of any rectangle is always simply just the length multiplied by the width. So here, the area is the length. Now what do we call the length? Let's go back a second. We call the length x, and the width was y, but we've just proven that y equals 10 minus x. So we're just substituting in the value of y, which is 10 minus x, so getting y in terms of x. Expand this out, we get 10x minus x squared, which again is what we wanted to prove. And so we've just smashed question 2 out of the park. Whoopsie. Whoop whoop. Not whoopsie, I mean whoop. Anyway, I'll stop talking rubbish. Question 3. We've got a semicircle below, has a perimeter of 20 meters. We need to show that x equals 20 over 2 plus pi. And so, perimeter of a semicircle, let's just call this perimeter P. Well, it's going to be comprised of 2 different parts. First of all, we're going to have a perimeter of the curved bit. That's going to be half of the circumference. And we're also going to have the straight edge here. So you can just think about this piece by piece. So you can have 2 different bits. So the yellow bit I've just coloured in is going to be half of the circumference. So if the radius here is x, then the circumference would be 2 pi times the radius. Normally we say it's 2 pi r. We now say here it's 2 pi x, because r is x. But of course this is only half the circumference, so I need to divide this by 2. And plus on the straight edge, which is going to be the diameter, which is going to be 2 multiplied by the radius, which in this case is 2x. So 2 pi x divided by 2 just gives us pi x, then obviously plus 2x. So we can factorise out here an x, which gives us 2 plus pi. However, we were told what the perimeter was. Once again, we were told again the perimeter is 20. So if we just substitute in for p the value of 20, we get that 20 equals x brackets 2 plus pi. And so if we just divide through both sides by what's in the brackets, 2 plus pi, we get therefore that x must be 20 divided by 2 plus pi, which once again is what we wanted to prove. So that's question 3 sorted. Lastly, for the warm-up, question 4, we've got a function is defined as 1 over x squared, x not being equal to 0. We now need to sketch a graph of the function y of f of x plus 3 minus 2. So I'm just going to get ready our coordinate axes. So if I just have a y, whoops, that's not what I intended at all, that's slightly slanted. There we go. And an x as well. So do the x-axis going across. We'll call this obviously x and y. So this is just harking back to transformations of graphs. So if we have f of x, let's first of all consider what f of x plus 3 would be like. So I'm just going to swap our input, which used to be x, for x plus 3. So whatever the input is, we do 1 over it squared. So if our input is x plus 3, we're going to do 1 over x plus 3 all squared. So this is going to have an asymptote at minus 3. So if we imagine the original function 1 over x squared, this is going to shift it back 3 units. So we've done f of x plus 3. So now imagine f of x plus 3, all of that minus 2. So what we're going to have here is the whole of f of x plus 3, which is 1 over x plus 3 all squared, but that whole thing now minus 2. So what I'm going to do here, I'm just going to take this y-axis, going to extend it slightly. Okay, so if we have a brief sketch, first of all, of what 1 over x squared would be. Now, 1 over x squared can only ever be positive. So if we imagine f of x here, when x gets close and close to 0, this explodes towards infinity. As x gets bigger, it goes closer and closer to 0. So we'd have here something like this for our graph of f of x. So first of all, that's going to get shifted 3 units back, and so we're going to have an asymptote where x is equal to minus 3. Remember, when the change happens inside the brackets, the change is the opposite to common sense. So instead of it being shifted 3 to the right, it goes 3 backwards. So first of all, I'm just going to draw in here an asymptote line when x is minus 3. And going back to our original function, f of x, it could never go beneath the x-axis, because imagine a big number here for x, say 100. F of x would be 1 over 100 squared, which would be 1/10,000th, but it's still going to be positive. And so we'd also have a horizontal asymptote for our original function, which would be the x-axis. However, because we've now shifted this down by 2 units, the new asymptote going horizontally would be at minus 2. So if I just draw this in going across, we'd also have a horizontal asymptote at y being minus 2. And so just sketching this here as well as I can, we then curve away down here, like so, and the same at the other end. As you can see, my sketching is absolutely pants. And would go towards but never touch minus 2 at the other end. That is pretty heinous. Again, that should be a smooth curve. Mine looks like I've got some sort of dodgy sort of hand going on. Again, I'm not today shaking in my hand, but you could be forgiven if you're thinking I am. That should be a a smooth curve. Again, check Desmos if you'd like, and you should see that it's got the same characteristic shape. Again, apologies for my lack of a smooth curve drawing. So this isn't in the notes. I just wanted to run through just to clarify last lesson, which was quite a slog. It was a 53-minute video, I believe. So I just want to just run you through the key points. So it was about the second order derivative. So imagine that we have f of x, which has a stationary point when x is equal to a. We said that if a second order derivative at a yields a value which is greater than 0, it's going to be a minimum. If a second order derivative at the stationary point a yields a value less than 0, it's a local maximum. We also mentioned this thing about a point of inflection, so I'm just going to can this for the time being and focus on the two top points here. Now I do think this is counterintuitive. It's a minimum when the second order derivative is greater than 0, yet it's a maximum when the second order derivative is less than 0, so it seems almost back to front. So I want to just use the graph of y equals x squared to give a bit more flavour and a bit more understanding to this. So first of all, I want you to imagine we have y equals x squared. Differentiate that, dy by dx would be 2x, and the second order derivative, d squared y over dx squared would be equal to 2, which is a constant. So first of all, as shown you here, imagine that x is minus 2, the gradient of a tangent would be minus 4. Again, 2 times minus 2 is minus 4. The point being, I want to try and show you what this second order derivative actually means in a practical example. So next along, imagine when x is minus 1, the gradient is minus 2. When x is 0, we have the stationary point, which is a minimum, as you can see. When x is 1, the gradient of a tangent is 2. And when x is 2, the gradient of a tangent is 4. So let's put this all together. You'll then hopefully see, looking at the tangents at different points, the gradient's gone from minus 4 when x is minus 2 to minus 2 to 0 to 2 and then up to 4. And so each time as we move along, the gradient of a tangent is increasing. So minus 4 plus 2 gets us to minus 2. Minus 2 plus 2 gets us to 0. Plus 2 and then plus 2 again. You can see that the gradient of the tangent is increasing as x increases, and so that's where this 2 comes from here, and so that's why it's a minimum point. It's starting as negative, but if a negative increases, it will at some point cross and equal 0. So as the gradient of a tangent is growing, positive second order derivative, that's why it gives a minimum point. So again, if we think of y equals minus x squared, then again differentiate this, dy by dx gives us minus 2x, and the second order derivative here would always be a constant minus 2. Now the second order derivative isn't always going to be a constant, it could be a function of x in itself. So again, just taking some points along the curve, when we have x being minus 2, the gradient is positive, get gradient of a tangent being 4. As we move along, the gradient of a tangent becomes 2 at x equals minus 1. We have a stationary point here which is a maximum when the tangent gradient is 0. Then the gradient of a tangent becomes negative. When x is 1, the gradient of a tangent is minus 2. And when x is 2, the gradient of a tangent is minus 4. So putting this all together, we can see here that the rate of change of the gradient, the second order derivative, is negative 2. That means for every unitary increase of x, the gradient of a tangent is decreasing by minus 2 each time. Yet as you can see, despite the gradient of a tangent decreasing each time, that relates to the stationary point being a maximum, because a tangent is starting off being positive, but it's decreasing and decreasing to a 0. That's when it tops out as a maximum, or at least a local maximum. Then it becomes negative on the other side. So positive gradient, 0, negative correlates to being a local maximum. So I hope that gives some clarification as to what the second order derivative means in practical terms, and also why, when the second order derivative is positive, it gives us a local minimum. When the second order derivative at a point is negative, that relates to a local maximum. So let's have a look at some real-life modelling with differentiation. And so we can think of dy by dx as the rate of change of y with respect to x. And so in terms of a graphical approach, the rate of change is, of course, the gradient. However, y and x don't need to be on a coordinate axis. They could just represent variables in real-life contexts, such as quantities. And in that case, you can use derivatives to model many real-life situations involving rates of change. So just picking this one out here as a little example, imagine the volume of water in this water butt constantly changing over time. So if V represents the volume of water in the water butt in litres and T represents the time in seconds, then V could be modelled as a function of T. In other words, the volume changes as T changes, and so V relates to T. And so if V is a function of T, if V equals f of T, then we could say that dV by dt, the rate of change of the volume with respect to time, would be f dashed of t. So that would be the derivative with respect to t. That would represent the rate of change of volume with respect to time, where time is measured in, for example, here, seconds. And so dV by dt would be the unit of volume, litres, divided by the unit of time. So it'd be litres divided by seconds. It'd be litres per second. So let's just have a go at practicing one with this example. So imagine modelling with differentiation now in terms of a rectangle. Length x and width y has a perimeter of 20 and an area A. So just this first line here, that should hopefully remind you about a question we attempted together in the warm-up. So x and width y, perimeter of 20 and area A. Hopefully that's reminded you of the warm-up questions 1 and 2. Okay, so what I'm going to do here is just return to what we had from questions 1 and 2 in the warm-up about this rectangle that had length x and width y, and it's here. Okay, so I'm just done this just to speed things along so we don't necessarily talk through the same things. And as well, it just shows you that sometimes warm-up will relate to the lesson coming up. And so we had length x, width y. We derived the width in terms of the length, y in terms of x was 10 minus x. And of course, the area of the rectangle, of any rectangle, is length times width, in our case, x multiplied by y. But of course, y is 10 minus x, which gives us 10x minus x squared. And so what we could do, and it can't hurt too much to do now just before we get the ideas cemented in our heads, is to actually just imagine a sketch of how 10x minus x squared, how the area varies. So if you imagine area on the y-axis and x going along, we could map the area as a function of x, like I have done here, using, of course, you could probably guess, this is from Desmos. So in the factorized form, we can see that when x is 0, the area would be 0, which makes sense. If a rectangle has no length, if x was 0, it could have no area. And at the same time, if x increased all the way to 10, it just become like a line. Y would have to be shorter because as x lengthens, y would shorten. So between 0 and 10 are where the area would become 0. And obviously it's going to peak somewhere here. And so by graphing it out, it also helps us to see that it's going to be a maximum when this function is at a stationary point. And so just to clarify, this here is x, and the y-axis I'm just going to call a, where a equals 10x minus x squared. And so where is a maximum? Well, there's two things we can do. Just going back to the other topic we did much earlier in the year on quadratics, you should know that if we know the x-axis intercepts of a quadratic curve, we can use the symmetry of the quadratic, and we can know therefore that the minimum or maximum, the turning point of it, will be halfway between the roots. And so if we have a root at 0 and 10, we should find that the maximum point here is where x is 5. So let's just see if the calculus, if this process we're going to do now with differentiation gives us the same result. So we'd imagine when x is 5, that's going to be the maximum point. So anyway, we're not doing it as a quadratics lesson per se, we're using differentiation here. So let's just see what we get from this. So we'd expect the maximum area when this gradient is at 0. So that's when dA by dx, it's not dy by dx, here on my y-axis I've labelled it a. So when the gradient is equal to 0, dA by dx is equal to 0, that's where we'd find our maximum. So anyhow, we've got what the area is. The area is 10x minus x squared. And so if we differentiate this, we'd get dA over dx. So 10x becomes 10. And differentiate the x squared term, bring the 2 to the front, so we get minus 2x to the power 1. So we can set dA by dx equal to 0. So therefore it's at a max when dA by dx is equal to 0. dA by dx is 10 minus x, and so when is 10 minus 2x equal to 0? Well, obviously, simply rearranging this formula, we get that x must equal 5, which is what we guessed it would be anyway. So it's just nice to show that no matter which approach we use, we get the same solutions. And so the maximum area occurs when x equals 5. Now, we want to justify, getting back to this question, that the area found is a maximum. So we know for definite when the gradient is 0, it's going to be a turning point. So it's going to be a maximum or minimum, we'd imagine. But can we prove that it's a maximum? Now this is where we're going to go back to the second order derivative. So like I mentioned before, when the second order derivative at a given point is less than 0, that proves the stationary point is a maximum. So let's find the second order derivative of a. So we had dA by dx, therefore the second order derivative will be d squared a over dx squared. So if we differentiate again, if we differentiate this derivative, 10 vanishes, minus 2x just becomes minus 2, which is a constant, so minus 2 is less than 0. So that proves that when a is 5, my apologies, when x is 5, the area is a maximum. And of course, just to make sure we actually answer the question like we're asked, we need to find what this maximum area is. So therefore, the maximum area, A max, we just substitute in x equals 5 into our function of A. So the area is 10x minus x squared. And so 10 lots of 5 minus 5 squared gives us 50 minus 25, which would be 25. And the units, I've just forgotten. Oh yeah, the centimetres. So the maximum area will be 25 centimetres squared. And that's when x equals 5. And so when x equals 5, just remember y would be 10 minus 5, which would be 5. So the maximum area of any rectangle with a fixed perimeter is when that rectangle becomes a square. So that's the general result. To maximise the area of any rectangle, contrive it so that it becomes a square. So the width is the same as its length. Question 2, another worked example. We've got here a large tank in the shape of a cuboid is going to be made from 54 square meters of what we're calling sheet metal. So by sheet metal, we're not saying that the quality is anything less than great. It's not sheet in that way. We're saying it's a roll of metal which is very thin. So as the same way you get like a roll of, say, toilet paper, you have sheets of toilet paper. So that's all it means by sheet metal. Anyway, the tank has a horizontal base, so it's lying flat and no top. The height of the tank is x meters, and the two opposite vertical faces are squares. So first of all, show that the volume of the tank is given by this relation here. So what I'd suggest definitely to do would be to do a sketch of this tank. It's hard to picture without doing a sketch. So it's a cuboid, we know that much. So what we can do is imagine the front face, imagine the back of it here. So then imagine the front being joined to the back, like so. And then also remember what the question told us. So what the question told us is that the two opposite vertical faces are squares. So we just need to think about it slightly carefully. Two opposite vertical faces are squares. All that means is that this face here is a square. Just an excuse for me to colour in like I'm a child. But still, it doesn't hurt to colour in from time to time. So if that's a square, the opposite facing face will also be a square as well. After we've done this, we can then label in the dimensions which we'll need for later. So let's just think about what else we're told. So we're told that the height of it is x meters, okay? So let's label in the height. So the height here is x. And because this is a square, we also know that if the height is x, then this width must also be x. We're not told what the that x is a bit wonky. Forgive me. There we go, a bit better. We're not told what the length is, but if we've got the height and the width as x, I'm just going to say and suggest we could say that the length of it, let's just call it y. Like so. So then we can think now, for part A, what the total surface area is going to be. So the total surface area of this tank, well, we're going to have these two faces, which are going to be x squared here and x squared on the other side. So that's where the x squareds come from. And as well as that, we're going to have the base. The base is y times x, or x times y in alphabetical order. Now, the front of it is y long and x high. So again, this is going to be x times y at the front. And because it's a cuboid, the back side of it will be the same shape and size as the front facing side. So xy for the bottom, xy for the front face, xy for the back face. And so here we have 2 lots of x squared plus 3 lots of xy. And we're told that the surface has been made from 54 square meters of sheet metal. And so that must be the total surface area. So total surface area must be 54. So we now have 54. I was going to write 52 there for some bizarre reason. Apologies. So 54 equals 2x squared plus 3xy. Now, again, just remember, the y was a figment of my imagination. We've been given this in terms of x. And so what we need to do is just think about what y would be in terms of x. And so if we just take this expression here and rearrange it in terms of y. So therefore, what we'd have y as being 54 minus 2x squared, all divided by 3x. And so just by taking y, which we have here, and rearranging it, we get that y is equal to this expression, getting y in terms of x. So now we can just move forward with this. So what we can say here is the volume. Now for any cuboid, the volume is going to be the length times width times height, isn't it? So that's going to be length times width times height. So it's going to be x times y. So we're going to have x squared y. But now, of course, we know what y is in terms of x. So that's the same as x squared multiplied by 54 minus 2x squared all over 3x. Like so. And so if we just expand this out each term, so 54 over 3x multiplied by x squared, well 54 over 3 gives us 18, so this would be 18 over x, multiplied by x squared, that would leave us with 18x. And if we multiply out this one here, minus 2x squared divided by 3x, this bit here would be minus 2/3 x. So minus 2/3 x multiplied by x squared, that would give us minus 2/3 x to the power 3. And so that's part A done. So part A wasn't the most straightforward thing in itself, but that's how we derive the expression for the volume in terms of x. So that's part A completed. For part B, we're told that because x can vary, can we use differentiation to find the maximum or minimum value of v? And so for part B, what we need to do here is to differentiate the volume with respect to x. So for part B, we need to find how the volume varies with respect to x. To do dv by dx tells us the rate of change of the volume with respect to x. And so we just differentiate the volume here, this function, with respect to x. And so the 18x, that becomes just 18. And the minus 2/3 x cubed, we bring the 3 to the front, so it multiplies for 2/3. So minus 2/3 multiplied by 3, just gives us minus 2. And we drop the power of x by 1, so x cubed becomes x squared. So this is going to be a turning point, that be a maximum or a minimum, when dv by dx is equal to 0. So let's just say this equals 0 when v is a maximum, or indeed when v is a minimum, but we're going to come to that in part C. So let's solve this for when v is a maximum. So therefore we have that 2x squared equals 18. Therefore we'd have x being plus or minus the square root of 9. Now just take a step back and just think to ourselves what x actually represents in our case. X is a length, and so we need to reject the negative root of this. We need to just go for the positive root of 9, which is 3. So maybe just make a little note. X can't equal 3, as x is a length. That's just showing to the examiner that you've considered the negative root and rejected it through consideration of what x is representing, rather than just guessing it must be the positive root. And so x must be 3 when v is at a maximum. So therefore we can actually work out what this maximum value is. So Vmax, again we're assuming at this time that it's a maximum, is when x is 3. And so the volume is this thing here. So if we substitute in when x is 3, we'd get Vmax is 18 multiplied by 3 minus 2/3 multiplied by 3 squared. So again, with a calculator, or otherwise, 18 times 3, that gives us 54. And minus 2/3 times, oops, that should be 3 cubed. Apologies for, oops, 3 cubed. Yeah, that's a cubed. This should be a cubed. So trying this on the calculator here. So 18 times 3 minus 2/3 multiplied by 3 to the power 3. That gives us a volume for this of 36 meters cubed. Now we need to just remind ourselves of what part C asked us to find. So if I just scroll up for a second, part C said justify that the volume of V we found is in fact a maximum and not, for example, a minimum. So to prove that this is a maximum, what we do is we need to take the second derivative. So if we differentiate again to get d squared v over dx squared, we now just differentiate this again. So the 18 will vanish, the minus 2x squared, the 2 comes to the front, makes the minus 2 a minus 4, the power of x drops to power 1. So d squared v over dx squared is minus 4x. So when x is 3, the turning point value for x we've just found, d squared v over dx squared is going to be minus 4 lots of 3, which is negative 12, and negative 12 is of course less than 0. And like we talked about earlier in this video, when the second order derivative at the turning point is negative, that proves to us that the turning point is at a maximum. So the stationary point here is a maximum. So therefore, V, which is 36 meters cubed, must be a maximum, not a minimum. If we computed this here and got a value which was greater than 0, that would prove that the volume was a minimum. But because it's less than 0, V is at a maximum for this point. Lastly, this is question 3, and this was actually a past exam paper question. So the manufacturer here is producing pain-relieving tablets. God bless their soul. Each tablet is in the shape of a solid circular cylinder with base radius x millimeters and height h millimeters as shown. Given that the volume of each tablet has to be 60 cubic millimeters, first off, try and express h in terms of x. So let's just take it back to GCSE, the volume of a cylinder. So the volume of any cylinder is the area of the circular top or bottom. So that's going to be pi times radius squared. Here the radius is x, so it's going to be pi x squared multiplied by the height, which is h. So we know that the volume has to be 60, so we can input this into our expression for the volume. So first off, we can now say that 60 equals pi x squared h. Now we can rearrange this to find h in terms of x. So therefore, just dividing through both sides by pi x squared, we get h equals 60 all over pi x squared. So if you wanted to, you could leave it in this form, which is easy to manipulate with calculus. We could have said, well, h equals 60 over pi. This will be a constant because 60 is a constant, as is pi, and we could say that's x to the power minus 2. But this is a more natural way to write the expression. Part B. Show that the surface area of this tablet is given by this expression here. Now this one is slightly harder, but not so bad. So the surface area is going to be the area of the bottom plus area of the top You wouldn't have to write it down like this in the exam. I'm sort of laying it on a bit thicker so you can see where these expressions are going to come from. Area of the bottom plus the area of the top plus the curved surface area. So the area of the bottom is just the area of a circle, which is pi times the radius squared, which is x squared. The area of the top is going to be the same. Now this curved surface area, if you imagine this circumference being unravelled, so imagine this being unravelled into a straight edge, what we'd have is a rectangular shape. So this would be the circumference, which in our case would be, circumference is pi times diameter, yes? So that's 2 times pi times radius. So that would be 2 times pi times x. And the height would still be h. And so the curved surface area is 2 pi x multiplied by h, which is going to just be 2 pi x h. So, however, we did have an expression for h from earlier, so I'm just going to colour code this so you can see where it's come from over here. So that's a curved surface area. And of course the area of the bottom and the area of the top was indeed the area of a circle. But from before, we have now got an expression for h, and so pi x squared plus pi x squared is 2 pi x squared, and h, let's just put 2 pi x for now. From before, if I just toggle back for a moment, h is 60 over pi x squared, so we can now substitute this in. So we still have 2 pi x squared. Now, we can simplify this quite a bit. So pi times x will cancel the pi down here, and we'll cancel off one of these x's, which we're dividing by. 2 times 120 is 2 times 60, it gives us 120. The pi's will cancel. X divided by x squared will just leave us with 1x at the bottom, which is what we wanted to prove all along. And so that's part B done for us. So the surface area of this cylindrical tablet is 2 pi x squared plus 120 over x. Part C, we now need to use calculus to find the value of x for which A is a minimum. And so we've just worked out what the surface area A was. So let's just recap what we had for A. And so A equals 2 pi x squared plus 120 over x. Now if we just write this in index form to make it easier to manipulate, we have 2 pi x squared plus 120 x to the power minus 1. And so the value of the surface area is going to be a minimum or a maximum when we find out where the dA by dx is 0 for the function. So if we work out dA by dx and find when this is 0, well, if we differentiate the 2 pi x squared part, the 2 comes to the front, so 2 pi becomes 4 pi. The new power of x reduces from 2 down to 1. Over here, the minus 1 comes to the front and multiplies the minus 120. And so we get minus 120. The power of x reduces by 1, so minus 1 minus 1, that now becomes minus 2. And so we now set this expression equal to 0. So when is 4 pi x minus 120 x to the power minus 2 equal to 0? Now this form here isn't in a very easy way to solve for x, but because this other side is equal to 0, we can use this to our advantage and just multiply both terms by x squared. So multiplying through by x squared, we have 4 pi x cubed. Multiplying this by x squared will cancel the x's altogether, so we have minus 120 equals 0. So rearranging, if we add 120 to both sides and divide through by 4 pi, we get this. Now if we cube root both sides, we get that x must be the cube root of 120 over 4 pi. Now that's not one for mental arithmetic, so bust out the brilliant ClassWiz calculator and let's see what we get. So shift root, the cube root of 120, over 4 shift pi. To 3 sig figs, we get 2.12. That's going to be in millimeters. And so the area, the surface area when this is minimized, is when x is 2.12 millimeters. So now at this stage, obviously, we knew that dA by dx is going to give a minimum or maximum. We've assumed it's a minimum. Now that ties into part D. Part E. We're going to show this as a minimum later. For part D, calculate the minimum value of A, giving your answer to the nearest integer. So we worked out the value of x, which gives a minimum, which is 2.12. So we're just going to sub in x equals 2.12. But as I mentioned in class, to make sure we don't have any rounding error, just let's give this to more significant figures. Let's go for 2.1216, say. 2.1216. Now it does say here we're going to round this off to the nearest integer anyway, but it's not a bad habit to get into to get our answers to more accuracy until we round off finally. So the minimum value of A, well, the expression for A, if we just remind ourselves, A, the surface area, is 2 pi x squared plus 120 over x. So that's going to be 2 pi times 2.12 blah 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 all squared plus 120 over 2.12, etc. Now in fact, I've just had a thought. You can use your calculator to just cut through a lot of this legwork with inputting lots of decimal places. What we can do here, because we had an answer of this, we can just use the ANS function. So if I just do now 2 shift pi multiplied by that answer squared plus 120 over the answer, which was the 2.12 and so on, we get 84.84 and so on. 84.84, yeah. So because we want to give this to the nearest integer, that rounds to 85 square millimeters. Now again, I have said for part C and just now, is this definitely a minimum or could it have been a maximum? So for part E, we're going to show and prove that this value of A is a minimum by differentiating again to get the second order derivative. And so from before, we had that dA by dx was 4 pi x minus 120 x to the power minus 2. So if we find the second order derivative of this, d squared a over dx squared, 4 pi x just differentiates to 4 pi. Minus 120, the minus 2 gets brought to the front, so minus 120 multiplied by minus 2 gives us plus 240. Minus multiplied by a minus gives us a positive. And the value of x, sorry, the power of x I mean, it gets reduced by a further one. The minus 2 becomes a minus 3. So now we can substitute in the value x equaled to 2.12 roughly, and see what d squared a by dx squared is for that value of x. So d squared a over dx squared, we can do this now as well. We can do a line and say x equals 2.12. Just a bit more notation. So that means we're evaluating the second order derivative line, which means when x is 2.12. So we get 4 pi plus 240, 2.12 to the power minus 3. Now you might be thinking, well, why hasn't he rounded this to more significant figures, because this isn't the final answer? Well, when we do the second order derivative in this case, we're not so hung up about the exact value. All we're concerned about is the sign of the second order derivative. So if it's going to be a positive, it's going to be a minimum. If it's going to be a negative, it shows that that value of a was a maximum. So let's just compute this now with our class whizzes. So 4 pi, get this out of the way of my writing, put it over here. So 4 pi plus 240 brackets 2.12 to the power minus 3. And we get there about 37.8. So 37.8. The main thing is that's a positive value. That's greater than 0. And so this stationary point, where x is 2.12, has a second order derivative which is a positive value. When the second order derivative is a positive value, we now know that that shows that that stationary point is a minimum. So therefore, when a was 85 millimeters squared, which is when x is 2.12, we now know that must have been a minimum. So that was quite a few marks in the real thing. That was from an old spec question. So quite a lot of work there, which is all the more reason you need to practice these yourselves now and having a go at these exercises. So if you try now for me, please, exercise 12K on page 281, try the whole thing. And again, I will say, please do let me know if you're struggling. Please do comment in the comment section or email me back. I'll do my best to go through some questions with you and give you some help. But again, if you're not doing this, then I can't help you to understand it in the first place. So try those, please. I'll be in touch again with another video or an email. So take care of yourselves, and I'll be in touch soon. Thank you very much for listening.